So in this podcast, what I want to do is to start off by calculating the area of the sides of a cone, and having done that, to describe what a frustum of a cone is and calculate its area. So let's look at our cone here. Here's some notation. I'm going to say that the length of the side is capital L. I'm going to say that the height of it, if you drop a line straight down from the middle to the base, is capital H, and I'm going to say that the radius of the base is capital R. Now, if you think about the fact that from the top of the cone, any line going down its side straight to the base, to this edge here, has length L, so it's a common length. That tells you that if you were to take this in paper and say put in a pair of scissors and cut up here, or any other line straight from the edge to the top, what you would get when you unfolded it would be part of a circle. You'd have a flat sheet of paper, and that flat sheet of paper would have a common distance from the top here to the base, and the base being this distance here. So I'm going to draw it like this. This distance here we've called L, so this distance is L, and since it's constant, this is mapping out part of a circle, so this distance is L. And the natural question to ask ourselves is, what is this length? And this length is the length of this circle, the circumference of this circle of radius capital R, and the circumference of a circle of radius R is 2 pi R, so this distance is 2 pi capital R. So we see that if R and L were the same, we would have a complete circle, but generally they're not. This is not going to be a full circle. So what is the area of a circle of radius L? So the area of a circle of radius capital L is pi L squared, but this is of a full circle of radius L, and at the moment we have only got part of it. We have a fraction of it, so all we need to do is to take this area and multiply it by the fraction. So if we have the whole circle, we multiply it by 1. If we have half the circle, a semicircle, we multiply it by a half, etc. Now, how do we know what fraction of a circle this is? Well, this distance is 2 pi r. The circumference of a whole circle would be 2 pi l, because l is the radius of this object. So we just need to say that our fraction is 2 pi r over 2 pi l. And of course these 2 pi factors will cancel in a minute, but this tells us what part of the circle we have. And this is the area of our cone. So let's immediately make some simplifications. So first of all, let's cancel the 2 and the pi. And then here we have a factor of L squared, and here we have a factor of L. So they're going to cancel as well in part. So the L cancels with one of those two, leaving us with a factor of L overall. So this tells us that the area of our cone is going to be pi L R. And that is our result for the area of a cone. Now we're going to use this result on the next page, but before we do that, it's perhaps quite nice to look at the following simple check. So let's consider our original drawing of the cone. We have a height h here, a base radius r, so these are at right angles since this is straight down to the center of this circle. The length here is L, so we can see that inside this cone there is a right angled triangle, and by Pythagoras' theorem we see that L squared is h squared plus r squared. So just rearranging that, what we see from Pythagoras' theorem is that we can write that r squared is L squared minus h squared, and since these are all positive quantities, they're lengths of distances in the cone, this tells us that r can be written as the square root of L squared minus h squared. So this means that we can rewrite our area of the cone as written here as pi times L times this square root factor for r. So we have pi L root L squared minus h squared. And you can see from just looking at the diagram that L is greater than h, but supposing we make h smaller. So in other words, we're bringing down the top of the cone towards this circle here. In the limit, as h tends to 0, our cone is going to be becoming flatter and flatter, and eventually, as h goes to 0, you are just going to have a circle. So we note as h tends to 0, our area is tending towards pi times L, and now this square root as h goes to 0 is the square root of L squared, so it's L, so we have L times L, so we are left with L squared. And this is the area of a circle, and that's exactly what we should expect as our cone becomes flatter and flatter, tending to a circle, and the radius is going to be L, or if you wish the radius will be R, but again you can see from this that R is equal to L as h goes to 0. So this is the result you'd expect. It doesn't prove this result's right, but it's a nice check to see that it works. So on the next page we're going to use this result for the area of a cone drawn in this way, and then we'll use it to calculate the area of a frustum. So let's go to the next slide. So what we've seen on the previous slide is that if we take a cone like this, the area of the side that I'm shading here in yellow is given by pi times L, the length here, times r, the radius of the base. So we want to use this now to calculate the area of the sides of a frustum, so let's think what a frustum is. And a frustum is a cone where you have chopped the top off. So if I take this cone and I just chop the top off it, I am left with a frustum. So let me now just try to draw what I mean. So let me draw a larger cone like this. I'm going to give it the same lengths, capital R, and this distance is going to be capital L. And what I want to do is I want to chop a slice off through it, and that's going to leave me with a circle at the top because the slice is going to be parallel to the base. So we have a circle here and a circle here, and I'm going to choose to call the radius of this slice here little r. Now the total length here is capital L, but we also want to have a name for the side of the frustum here, and I'm going to call that little l, and then we have this length here, and that is capital L minus little l, but it's going to be helpful just to give that another name, so I'm going to call it L1, and clearly L1 plus little l is going to be equal to capital L. And our strategy for calculating the area of a frustum is going to be to calculate the area, or to use this formula rather, for the area of the whole cone and then subtract from it the area of the smaller cone, and that difference of the areas is going to be the area of the frustum. To mark the frustum more clearly, let me shade this in black, and then down here and here and here and here. So this is our frustum, and again I can just show a little bit more clearly this way. This is the area that we are trying to calculate. So this is the frustum, and I'm now just going to make this a bit smaller so as to give myself some more room. So now the area of the frustum, which I'm going to call A sub f, is going to be the area of the whole cone, and using this formula here it's pi LR, but remember capital L can be written as L1 plus little l, so I'm going to say that we have pi L1 plus little l times capital R, so that's the area of the whole cone minus this area, and we use the same formula, but now the length of the side is not capital L, it's L1, and the radius of the base is not capital R, it's little r. So I have minus pi L1 little r, and now I'm just going to tidy this up a bit because I've got some terms with an L1 dependence, and I'm going to bring those together. So what I have is the area of the frustum is pi little l r plus pi little l1, and there are two terms that involve l1, pi l1 times capital R and pi l1 times little r, and that second term has a minus sign, so what I have is pi l1 brackets r big R minus little r. And that is our formula for the area of a frustum, and this is correct, but it is not a very appealing formula, and the reason for that is our formula involves L1, which is a length that is not part of the frustum. We'd really like to rewrite this in terms of lengths in the frustum, and we can do that as follows. So imagine looking at our frustum through the side and taking a slice right through the middle this way, down here. And if you looked at it through the side, then what you would see would be a triangle. So this is a slice through the middle of the frustum, what it looks like. And it has a distance here from the middle, capital R, and there is a distance in the middle here, little r, that's the two radii here and here, and this distance is little l1, and this distance here, the total distance, is capital L, but it's also L1 plus little l, so we can just write this as little l. So if we now consider our two similar triangles, this one here and this one, they have the same angle and they're both right angles, so these are similar triangles. We see from our similar triangles the following properties. So from similar triangles, we have that L1 over little r, say, so that is the ratio of this side divided by this side, must be equal to the ratio of this side divided by this side, and that is going to be L1 plus L, all divided by capital R. And now what we do is we take this equation and we multiply both sides by little r and capital R, so here we get L1 times capital R, and here we get L1 plus little l all times little r. So doing that and solving that gives us that L1 is equal to little r times little l divided by capital R minus little r. That's just a little bit of algebra for you to check. So we can now take this result, substitute it into our formula for the area of a frustum, and we will have the area purely in terms of lengths in the frustum. So let's see how that works. If I'm going to substitute this in here, I'm going to have pi times little r times little l times this difference, but in L1 we have exactly the same difference. Here it's on the top, here it's in the denominator, so they are going to cancel. So what we see is that the area of the frustum is pi L r plus pi little r times L. So this is pi, and it's now capital R plus little r all times L. And this formula for the area of a frustum is much more appealing than this one, and it purely depends on lengths in the frustum. The radius of the top, the radius of the base, and the length of the side little l. However, it is also possible to write this formula in a different way, which is also sometimes useful, and to finish this video, that's what I want to do. So what I'm going to do is to draw our frustum again. So I draw this triangle here, and I'm going to show our slice is here, and draw a dotted line right through the middle. And I would like now to say that the height of the frustum, in other words the difference from the top slice to the bottom slice, is going to be h, little h. This distance here is little r. This distance here is capital R. And now what I'm going to do is I'm going to draw a line parallel to the line through the middle, but starting here where our slice touches the edge of the cone, or marks the corner of the frustum here. So to do that, I'm just going to draw another dotted line here. It is parallel to this line and has the same length, little h, and we have a right angle triangle here, and this length is little h, and this length here is going to be capital R minus little r, and this distance along the side of our frustum is little l. So we have a right angle triangle, and we have all three sides, so that means we can write any of the sides in terms of the others, and I'm going to rewrite L here in terms of these distances. So just to make this a bit clearer, let me just mark out the sides of our frustum here. So by Pythagoras' theorem, what we have is that little l squared is equal to capital R minus little r squared plus h squared, which is, I emphasize again, the height of the frustum. And now we can just take this, we can take the square root of both sides. These are all distances, so they're all going to be positive, and we can replace L here by the square root of this. So this tells us that the area of our frustum, AF, can be written as pi capital R plus little r, that's this bracket here, multiplied by the square root of capital R minus little r squared plus h squared, where h is the height of the frustum. And this formula is an alternative way of writing the area of the frustum, and it is the formula with which I'm going to end this podcast. So just very briefly, to obtain this formula here, we first of all calculated the area of the side of a cone. This was our result. We then said a frustum is a cone with the top sliced off parallel to the bottom. To calculate this area, we calculated the area of the larger cone, subtracted the area of the smaller cone. We used similar triangles to work out how to rewrite L1 in terms of distances in the frustum itself, and then we obtained this result here, and then we just looked at this right angle triangle to rewrite this to get rid of L, the dependence on the side of the frustum, and to rewrite it in terms of the height of the frustum and the other lengths. And that gave us this formula with which we stop our podcast.